Go, the programming language, not the game. Most dev surveys have one thing in common. They all show Go as one of the fastest growing languages. Why is that? What makes Go so special in an environment filled with strong, well-established alternatives? The answer is simpler than you'd expect, and it will be obvious once we'll explore 7 of Go's top features and main selling points. Don't worry, these concepts are straightforward, and once you'll learn them, you'll probably be able to understand 80% of any Go codebase. For a bit of context, I've been involved in full-stack development for 15 years, with Java and Kotlin as my go-to options for building backends. During this time, I had the chance to experiment with many other languages, and Go is among the only ones standing a chance to win me over thanks to its power and simplicity. The most efficient way to learn a new programming language is to dive right into it, so let's take a look at a Go program. There are a couple of details and conventions you should be aware of from the get-go. Let's start by initializing a module, which will create a go.mod file in our directory. This is where we'll do our version control and dependency management. Next, I am creating a main.go file with a main package and a main function as the default entry point into our program. Here, I'm defining a scanner instance, which allows me to read user data and a slice of 5 string elements. Slices are a powerful concept we'll discuss in detail when we look at data structures. For now, just remember that this line creates an empty structure that is ready to hold up to 5 strings. Then, we'll use a for loop to read 5 values from the terminal and append them to our slice. These values are then sorted, iterated over, and printed back to the screen. A couple of things to note here. First, we are relying on the standard library quite a lot. This is common when working with Go, and the language is renowned for all the functionalities it comes packed with out of the box. Second, the Go compiler is strict and will throw an error if you declare unused variables. To bypass this issue, we can use the blank identifier. Back in the terminal, we'll run Go build to compile our code and get an executable file as a result. Quick side note, the Go compiler is really fast. This performance is achieved thanks to a concise type system, an efficient dependency analysis process, and other language features we'll discuss during this video. Besides the main function, we can define one or more init functions, which will be executed only once, before the main function, when the package is imported. This is a good place to load up property files, establish database connections, or perform any other setup tasks your program might need. Remember that init functions cannot be called or referenced directly. And since we are talking about functions, note that a unique and powerful Go feature is the ability to return multiple values from a function. Before moving to variables and pointers, let's also briefly discuss packages. All Go programs are organized into groups of files called packages. These allow code to be shared in smaller, reusable pieces. By convention, the name of your package should be the same as the directory containing it. Another convention states that identifiers starting with an uppercase letter will be exported and visible outside the package, while lowercase identifiers will remain private to the package. Next, let's see how we work with data in Go. If your background is in high-level programming languages, this is where you'll need to pay a bit more attention. One of Go's selling points is its support for pointers and working with the memory directly. This might seem scary at first, but you'll see that Go manages to find a balance between the power of direct memory manipulation and safety against common programming errors. Using the var keyword, we can define variables both at package and function levels. Remember that Go is strongly typed. You can use explicit type declarations, but most of the time, the compiler is smart enough to infer types when initializers are present. Inside functions, you can use short variable declarations for a more concise way of writing your code, and you can define values that can't be changed after initialization via the const keyword. Pointers, which are variables that store the memory address of other variables, can be created via the address of operator. Then you can still access the actual value behind the pointer with the help of the dereferencing operator. Unlike C or C++, Go doesn't allow pointer arithmetic, which is a common source of errors and vulnerabilities, and it is garbage collected, which means that memory management is mostly handled by the Go runtime. Pointers are a lot more useful when combined with user-defined types, but before looking at that, let's briefly review Go's main control flow statements. When it comes to looping, things are straightforward. The for construct can be used with an init statement, a condition expression, and a post statement. Both the init and post statements are optional, so you can drop the semicolons and replicate the see whiles behavior. You can also drop the expression to end up with a block of code that loops forever. Ifs are straightforward as well, but note that you can start with a short statement to execute before the condition. The defer construct might be a bit more novel, and it provides an easy way to postpone the execution of a function until the surrounding function returns. The deferred call arguments are evaluated immediately, but the function will be executed later. Moving to something a bit more involved, let's look at Go's type system. Remember that we are talking about a statically typed programming language, so the compiler has to know the type of every value in your program. Types provide two pieces of information: how much memory to allocate, or the size of the value, and what the memory represents. Go offers both a handful of built-in types and an easy way to create user-defined composite types via the struct keyword. We can easily initialize structs via literals either by passing in both the field name and the value, or just the value. We can also add behavior to our types via methods, but you might find this developer experience a bit weird at first. Methods are just functions that contain a receiver, which is an extra parameter declared before the function name. Note that this can be either a value or a pointer receiver. Understanding the difference between values and pointers is key to be successful with Go. Of course, basic types like int, float, or boolean are copied on assignment and are passed around by value. Structs, however, are far more interesting, so let's look at a quick example. I am defining a basic user structure with an age field and two methods, one with a value and one with a pointer receiver. When this code is executed, you'll see that only the second user will output the expected result. This is because the value receiver performs a copy of the struct inside the method, performs the mutation on the copy, but when the function finishes its execution and is removed from the stack, the old struct value will be back in the scope. You might have also noticed that the struct is a value, but the receiver expects a pointer. In such cases, Go adjusts the value to comply with the method receiver, so you don't have to worry about it. Before moving to data structures, we should briefly review Go from an object-oriented perspective. The main thing you need to know is that while Go does not follow the classical OOP model, it implements many of its key principles in a simpler, more flexible way. Remember that you can control the visibility of variables in Go through capitalized and uncapitalized identifiers. Polymorphism is achieved through interfaces, which are types that just declare behavior. When a user-defined type implements the set of methods declared by an interface type, the compiler will be able to automatically pair these types up when needed. When it comes to inheritance, Go doesn't support the traditional approach and relies on composition via type embeddings instead. Any existing type can be declared within another type, and then, through inner type promotion, identifiers from the inner type are promoted up to the outer type. Go also offers generic support, but this is a rather recent development. Because they aim for simplicity and readability, the language designers were reluctant to add in complexity that could potentially compromise these principles. As a result, despite the fact that Go was first released in 2009, it only got generic support in 2022 after a lot of pressure from the community and enough time and effort put into making sure that the Go principles are still followed. Next, let's discuss arrays, slices, and maps. In Go, arrays are a fixed-length data type that contains a contiguous block of elements of the same type. Once an array is declared, neither the data being stored nor its length can be modified. If you need a larger capacity, you have to create a new array and then copy the existing values. Slices can fix the capacity limitation since they are built around the concept of dynamic arrays and can grow or shrink based on your needs. Slices are three-field data structures that contain the metadata Go needs to manipulate the underlying array. Note that these are created through literals very similar to arrays with one small difference. No length is passed in the square brackets. Finally, maps are data structures containing unordered collections of key-value pairs. Go maps use hash tables under the hood, and there are various implementation details here worth exploring in a dedicated video. Please let me know in the comments if you are interested in more technical deep dives on such topics. Next, let's look at one of the more advanced concepts, concurrency. In short, concurrency in Go is the ability for functions to run independent of each other, and it is one of the many things Go excels at. When a function is defined as a Go routine, it is treated as an independent unit of work, and it gets scheduled and then executed on an available logical processor. This work is coordinated by the Go runtime scheduler, which sits on top of the operating system and binds operating system threads to logical processors that can execute our code. Of course, concurrent work may lead to race conditions, which happen when two or more Go routines have unsynchronized access to shared resources. To avoid this, read and write operations against a shared resource must be atomic. As an alternative, you can rely on channels, which allow Go routines to safely communicate and share data with each other. Finally, let's briefly talk about Go standard library. This is a comprehensive set of core packages providing various features ranging from basic programming necessities like logging to more complex topics like building HTTP servers or interacting with the operating system. Since these packages are tied to the language, they also come with a lot of promises and guarantees. If you've enjoyed this video, you should watch one of these ones next. Until next time, thank you for watching.